All right, it is 11:15. We'll get started. I was making a little news and updates separate video on YouTube, but I'll probably just incorporate it to the lecture class time because then I would end up doing it twice, and I thought that would not make sense. Um, but I'll still post all this on YouTube, of course, and this would be going into the lecture 28 folder because would be the technical topic of today, even though I'll be talking potentially about 27 as well. Last time we took an exam, the grades have been posted to Canvas. Please go back through and make sure all of the grading on Gradescope makes sense to you. If there's any issues, feel free to request a regrade and I'll take a look at it. I also in the email mentioned that I posted problems at 5. I posted recommended problems. And I also posted a list of topics for Exam 5, and this would be in the Exam 5 folder. The problem set is due on Monday, so this is coming up fairly fast. But again, we have a short section, and that means that we'll have another normal quote lecture on Monday, and I'll get that video probably posted by Friday. Exam 5 will be then on the following Friday. I've also moved office hours. They are now Wednesday and Thursday, so today and tomorrow, just so that these can align a little better with the exam and the problem set that will be due, so that I can address a few more questions on those if people have them. Overall, on the exam, people did better than average, so usually I'm trying to see a median somewhere between 70 and 72. Now the median was at 81.5. So good job on the exam, everyone. Whether there's a bit more time to double check answers, or maybe it was a little easier, or maybe other factors, I don't know. But at least this means that hopefully the new environment is not significantly impacting people's performance. And in looking at all the grades across the board, I didn't see too many grades that were significantly abnormal from where people usually were, if not a slight improvement. I will not do a full review of the exam, but there were a couple questions that were commonly missed that I quickly wanted just to mention. Oh, I forgot which number this. This is, I think, number 6. And so a few people missed this problem. A lot of people chose A. A is perhaps a little bit deceptive because it does have this CF3 group that you think is an electron withdrawing group. But by putting a CF3 group on the nitrogen, now we don't have any NH bonds. And that is usually our most acidic proton in the amide series. So that means the most acidic CH bond, hydrogen now would be this carbon-hydrogen bond, which would be much less acidic than something like an imide E that actually can... I could be looking in the wrong place. My exam on Gradescope says ungraded. I will make a note and check that. Do you have a grade on Canvas? Oh, I'm wondering. Let me try something. I think to ask my TA after I finish looking at them. Oh, I think he never published the grades formally. I think I just did it now. So I am sorry. I am sorry that they were not available there. All right. I think that should have been. All right, cool. It worked. Yeah, so I just clicked the button. I'm sorry. But again, back to this problem. So now you should be able to go and review some of the questions that you missed. I also posted the solutions to the exam with commentary. I think most of it should be pretty straightforward. Other than maybe a few of these. But the main idea here is there is no NH bond, so your most acidic one will be the one that can put the charge on 2 different oxygen atoms, as well as the nitrogen itself. Oh, this was 6. That means this one was probably 3 or 2. This is number 6. Which one reacts fastest with sodium hydroxide? There was, I think, one problem that threw people off. It was this one. So the way we want to think about the rates of attack on a carbonyl is how much ground state stabilization or how much resonance donation does a carbonyl have. So if we look across the board, we have E with 2 nitrogens donating into the carbonyl. A has an oxygen and a nitrogen. We go to something like D or B, they both have a single nitrogen, so they should react faster. B, of course, is sterically hindered than D, so that gets out of the way. And then we have C. C actually has a case where we have two different carbonyl groups. So statistically, if they were the same, this would be faster because there's two of them. But we also get an electronic benefit because we only have one nitrogen that's trying to stabilize two different carbonyls, so they only get half the stabilization each. So if you make the analogy to something like an anhydride, this is going to be more reactive than an ester because, again, there's only one oxygen for two carbonyls versus one oxygen for one carbonyl. So it's kind of splitting up its duties so it's able to stabilize that system a little bit less overall. And the final problem was the synthesis problem 12. One thing that was a qualifier that we could also see on sort of the template ahead of time if you looked, all the carbons needed to come from a single starting material. So if you went and used something like this aldehyde, you needed to actually make that aldehyde. Another fairly common response was to do something like make this amine and then react it with this bromide. This was, again, gets back to the problem with amine alkylations is that it's really hard to control them. So this was one of our methods for always making mixtures of products, and it wasn't an efficient amine synthesis, and that's why we developed many other methods like reductive amination or other strategies to go and make tertiary amines cleanly without having a lot of byproducts along the way. I think those were the main ones that perhaps had at least some consistent errors that I saw reviewing all the answers. But now let's move on to some of the new material. So just to briefly mention lecture 27, if people hadn't looked at this last time I mentioned this, we are now looking at carbonyl compounds as nucleophiles. This is because whenever you have a hydrogen alpha to a carbonyl, this now becomes much more basic. So we can use things like sodium hydroxide to make equilibria, to now make a negatively charged molecule called an enolate that is going to be nucleophilic at carbon. So the big theme here is we're always going to be having these arrows pushed down, and this will go and attack something. So in this case, we're going to have it attack one of its cells for this problem in a second. Now, I don't like that arrow. I'll show that in a minute. We found that we can do this under acidic or basic conditions. If we're under acidic conditions, we end up making a molecule that's called an enol. This is much less nucleophilic because it is uncharged, but it will be slightly nucleophilic at this carbon atom. We talked about when you go through these enols, these become flat, so they lose any stereochemistry. Since they are nucleophilic, you can end up halogenating them. So by reacting with things like bromine, we could have reactions still take place here. And we learned a special case called the haloform reaction. The main reaction we learned is the Aldol reaction. And this is a type of reactivity we're going to see really for the rest of this topic. This is one of the key reactions we need to know pretty well. And this is whenever we go and we make our enolates, these can also self-react. These will be able to react at carbon and then attack another carbonyl compound. So after proton transfer, we end up making a hydroxy carbonyl compound. And depending on the temperature, whether we're at low temperature or heated conditions, we can either isolate this hydroxy compound or we can eliminate it to the double bond. In the next lecture, we learned a bit more about aldols, limitations on controlling them if we have two different coupling partners. If we want to have selectivity by reacting one carbonyl compound with another one, essentially one of the carbonyls cannot be enolizable. That means it will not have a hydrogen next door to the carbonyl. So you could have something like benzaldehyde, and it would be able to selectively react with another aldehyde because there are no protons to deprotonate. So we can't self-react. It can't even react without something else adding to it. The big message we had, I think, or the next most useful thing is the idea of a lithium enolate made from LDA. LDA is this super strong base, super base. We know that we have these isopropyl groups that are really big and bulky, and this actually makes it not only deprotonate really fast, it's very selective in how it deprotonates, because it'll only deprotonate at the less sterically hindered side. We see that if we have LDA, it will only grab the hydrogen that is more accessible. It will go and give us a new lithium enolate, and the byproduct is diisopropylamine. So if we can compare the pKa of a cyclohexanone, that's around 17, and something like diisopropylamine, which is actually a little higher than ammonia, it's at 38. Because of these wide distinctions in pKa, this is effectively irreversible. So this means at low temperature, you can add LDA, it'll rapidly deprotonate your carbonyl compound, and it'll get pretty much stuck here until you add an electrophile or work it up with water. We won't have any scrambling of this, so we're able to control what will be the nucleophile. That means you can, depending on the order of addition of different components, we can deprotonate one carbonyl compound, then add it to another one without having to work on some of the selectivity issues. Someone asked what the average on test 4 was. That was on our first slide. The average was a 79. The median was an 81.5. So on the whole, people seem to do considerably better than average on the exam. And so from here, does anyone have any general questions about, I guess, the exam or different things? I have a series of Piazza questions that someone posted that I'm ready to go through, and I think they will be instructive for highlighting some of the sort of potential problems we can have, and I think reinforce some of these ideas that we were just discussing. Cool. Then I will start going through these. So this one question was, why do we not get elimination with LDA? So this is something that I mentioned, is if you go and deprotonate a carbonyl compound with LDA, unlike the case under heated aldol conditions, we will never get the elimination product out. So let's imagine we reacted this with some sort of aldehyde. So one of the reasons we observe elimination in aldol reactions is because there's a lot of proton transfers going on and there's a lot of equilibria. Yes, wait. No, I believe 29 as well, and there'll be a 30th lecture. Did I misrespond to someone on Piazza? Whatever is posted right now will give you enough information to do the problem set on Monday. Yes, because we're covering lecture 28 material primarily today. Lecture 29 would be the material for Friday, so that means you'd be able to have that in hand to do the problem set that's due on Monday. On Monday, there will be lecture 30 that would also be on the exam, and I'll provide extra problems on that content. And we would be able to review that on Monday, Wednesday. On Monday and Wednesday before the exam the following Friday. If I have all of my dates correct in my mind. So I was saying that with LDA, we get around a lot of these proton transfers. There's not water around. Essentially, we take a proton away irreversibly. And we essentially get stuck at this alkoxide stage. This alkoxide can't deprotonate itself. Geometrically, cannot do that intramolecular proton transfer. So usually these are at low temperature and also reduced protons available. These are the two reasons why we do not see elimination. A reduced number of protons. This means there's no water around. So usually, like in an aldol reaction, we have water as a byproduct, and this is something that is always going to be in equilibrium. It could be a proton shuttle, and this will kind of prevent this from happening. This will be stable at low temperatures. There won't be a lot of interaction between molecules self-deprotonating each other because they're all negatively charged. So you can't really make a dianion, and there's not another hydrogen available to start that equilibrium. Yeah, and these are usually about minus 78 degrees Celsius. Okay. And then there was another question where we were doing another aldol-like reaction, and they were unclear about how we got to these different intermediates. So I'll just go through the mechanism a bit more explicitly. This follows the exact same arrows as the aldol condensation that we I think have written out a bit more in the lectures. So first, sodium hydroxide will react with acetone. This will give us an equilibrium. We'll make a small amount of this enolate along the way. This enolate is able to then attack this aldehyde. We make an intermediate alkoxide, negatively charged. And then we have water around, because we just made it in the first step. That'll be able to protonate the alkoxide. I think you can, you could do that, just email me directly. Alternatively, I think there's a button to request a regrade within Canvas, so either one works for me. And now, since we still in this new product, we both have the same hydrogen on that alkoxide, so this is going to be a reversible reaction. We still have more sodium hydroxide around. And we have other hydrogens that can be deprotonated. So whenever you deprotonate this hydrogen, again, this will be in equilibrium. This will be an unfavorable equilibrium as well. That's how we get to the next enolate that then can finish the E1CB elimination and remove the hydroxide. And that would give you the initial first product of the first condensation reaction. You could follow the exact same steps potentially with another molecule of benzaldehyde. And would do a double addition. So depending on how many equivalents are stated, you could probably make either one of these pretty selectively. Cool. So here's some questions about the problem set already. So instead of probably giving you all of the answer right now, I'm going to just sort of suggest some things to think about. So in this case, I think the person had the right idea to have their alpha hydrogens removed by hydroxide and see how stable they are. And so this is certainly what you would want to do. You would want to imagine deprotonating next to these carbonyls in any of these cases. And then consider resonance isomers. See which ones have more or less. And then the main feature that's going to distinguish between these two types of molecules is actually going to be the difference in pKa between an ester and a ketone. So this has some similar logic to their relative reactivities. Does anyone know what's more acidic, an ester or a ketone? So the ester is going to be less acidic, and a ketone will be more acidic. So this is consistent with esters overall being less reactive than ketones. That still remains true. The way we kind of want to think about it is kind of goes back to this resonance stabilization idea. So we already have this resonance interaction taking place in a methyl ester or any type of ester. Whenever we go and deprotonate this, the main resonance structure form will put the charge on the oxygen, and now we no longer are able to use the protons or the electrons on the oxygen in resonance. So in effect, it's kind of breaking up the resonance along the way. So this leads to so again, it's sort of the greater lower ground state energy that deprotonation breaks up the resonance afterwards. And because of this, we also have another trend that comes in. So since esters are less acidic, that means that their enolates will be both more basic and more nucleophilic. And we can also think about this as now this lone pair of the oxygen sort of adding in to this double bond along with the other oxygen. So it makes this terminal carbon even more electron rich and more nucleophilic along the way. Oh, I think I just copy and pasted. Did I do this one already? Yeah, I think I just copied and pasted something. I apologize. All right, so this is also on the problem set, and they were having trouble trying to figure out how to do some of these cyclizations. Aldol cyclizations, we went through a number of cases. These ask usually pretty good questions on problem sets and tests because it establishes a lot of the main ideas related to carbonyl reactivity. In one case, they said they got a weird 6-membered ring and also not sure if the elimination was done correctly. So I hope they don't mind. I just copy and pasted the images from Piazza. And so this has the right idea, making the initial enolates and considering different paths of attack. One thing to note, though, was in this case, we want to be careful with numbering. So there's numbers 1, 2, 3, 4, 5, and 6. And then it went to a 6-membered ring. But along the way, we forgot to count this carbon at the end, because this one will be part of the ring, because this is where the nucleophilic attack happens. So we'd really want to be starting here at 1, 2, 3, 4, 5, 6. And we'd expect to make a 7-membered ring from this cyclization. So from this point, you could make the rationalization that 7-membered rings are slow to form. So there's probably going to be a better option. So rather than trying to draw that proposed structure, you may want to go and see if there's a 5-membered ring that could go and do an aldol condensation first, or otherwise you may be sort of taking quite a bit of time making sure you get the 7-membered ring drawn correctly. And the other one was, I'm not sure if I did the elimination correctly. And so this is a case from another cyclization. There actually, you would not be able to eliminate this alcohol. So enolates, we always want to imagine the electron flow. So if the oxygen start at the electrons start at the oxygen, they will have to push down to make a carbon-oxygen double bond. and this bond attacks. So we'd have to be making a new bond here. Alternatively, you can imagine an enolate in this resonance isomer, and this highlights the nucleophilic carbon maybe a bit more clearly. So the reason that we're not able to eliminate this hydroxide, if we were trying to do this elimination, we probably wouldn't want to take this hydrogen away. We'd be trying to take the hydrogen that's beta, because we always need to have electrons pushed down and over. But in both of these cases, we would not be able to eliminate this hydroxyl. So usually you're not able to eliminate hydroxides in E2 elimination cases. The scenario becomes special whenever we have a carbonyl compound. So in order to do these eliminations, we really need to have a hydrogen that is next to a carbonyl. So we need an acidic proton beta to the OH. So whenever we have this hydrogen here and we have a base, now we can fully deprotonate this. And this is always a two-step process. It's not a concerted elimination. We'd make our enolate, and the enolate generates first, and then we would have the elimination step afterwards. And it's because we're able to fully deprotonate the molecule first that we're allowed to eject this hydroxide. So if you consider the pK of water is 14 and ketones are up closer to 20, this is still going to be a downhill process. In this case, this hydrogen, its pKa is around 40, so no deprotonation. In this molecule here, there is a methyl group, so there are no alpha hydrogens. So this one would not be able to go to a double bond at all. And then you have to consider whether or not this would be a viable product. Usually one of the driving forces that push these reactions forward is the elimination of water. So there's probably going to be a better option as well from that stage. Okay, here is a series of questions. There will be an elimination, right? I would say that is a safe assumption. Based off of the sodium hydroxide heat, I would be looking for doing an aldol condensation of some sort and making sure you get that product correctly. The second question I do want to talk about a bit more. What does ethyl lithium do here? And so this is actually a pretty good question because we haven't talked about it much. Because now we're getting into this section where we have carbonyl compounds. And the beginning of this section talks about how these protons are somewhat acidic. And we also know that alkyl lithiums are very, very basic. So there's a question of, does it act as a base? Does it act as a nucleophile? So these will still actually react as nucleophiles first. This has to do with how, in reality, the lithium coordinates to the oxygen a little bit before these attacks. And so this will continue to do nucleophilic attack. So I'll let you determine what that structure should be. But this will be a nucleophile. We'll still have organometal compounds reacting as nucleophiles with carbonyl compounds. Once you get to lecture number 29, you'll see that there are some options and as to how some of these types of molecules can react with alpha beta unsaturated carbonyl compounds. So you may want to evaluate that too. I think for this question, you wouldn't need to see that. And the last Piazza question that we had was that I thought the product was formed from 3 propanol molecules. This is true. These 3 propanol molecules will go together, and I'll even give you a hint. You will be using an aldol condensation. I don't think I broke it apart correctly. I'll say that the retrosynthesis going back initially was pretty good. I gave one of the carbons 5 bonds. This is always a cause for concern, and I'll help you out with that soon. And I'm not sure I did the correct functional group manipulations. I would say your functional group manipulations seemed reasonable to me, but it is this step right here that we'll talk about. So this is the 5 bonded carbon that was referred to. And so it has to do with the connectivity of the product, because we have 6 carbon atoms coming from a 3 carbon atom unit and a 3 carbon atom unit. But we're going to end up kind of with a branch point, because if we imagine the enolate forming on one of these molecules and attacking the other, this would be our initial intermediate, where we now have one of the carbons go down and the other carbon is over here. So I think you were trying to use this central carbon as the nucleophile, and it should be the carbon next door. And then since we have heat around, we then can protonate this molecule. I think that was faster. And then hydroxide will deprotonate this molecule. Oh man, I'm so efficient. Maybe. And this will be able to go down and eliminate to give us the aldol condensation product. So I'll say that you can already kind of see some similarities between even this initial product and the product that we're going towards. And so your task is now to figure out this last segment, and to do that, I'll refer to lecture 29. Okay, that was all of the Piazza questions. Do people have any other questions right now that I could try to address? I know that there have been a number of people who have been emailing me either late last night or this morning. I've spent all my time trying to get these materials together and some other things. Sure, you can ask exam questions. Let's do it. I am prepared. I have the exam for solutions that I can copy and paste over and explain anything else. It was question 2. Yeah. Okay. For 11b, would SOCl2 also work? Let me go to... Oh, that's actually interesting. We did not learn that, and I don't even know if my TAs know that reagent works. So we did not learn that works, but it actually does. You can use thionyl chloride to dehydrate primary amides. There's actually a number of reagents that dehydrate primary amides. I might go take another look. Incidentally, there's some things that probably work here that you may put. If you put that down, I will give it to you. In some cases, there are some reagent combinations that would also work in combination with base. For 13, I'm guessing this was regarding this initial step. And this is one of the cases where I think this is consistent with things like reactions of sulfonyl groups, like tosol groups. This is something where I said I always disagree with the book and that it doesn't make sense for this to be an attack because this is a tetrahedral center. And the same is true here where we actually have a lone pair on this sulfur. So this is more of an SN2-like process. Is that the question that you had? Okay. Question 2. I talked about question 2 at the beginning. Beginning of class on the slides I had posted. So anything with a CH bond or anything with a hydrogen technically could be acidic. It's just how acidic. In some cases, an alkane would not be very acidic at all. We're looking for the ones that are the most acidic. In this case, imides are going to be the most acidic. This is because when you deprotonate them, they have a lot of resonance stabilization. And then an analogy is in class, we also saw phthalimide being deprotonated by just sodium hydroxide because its pKa is around, 9 or 10 and was given the same rationalization. Isn't it technically correct that an ester is being formed? I understand that it's more specifically called a carbonate, but it's an ester. I would disagree with that assertion. Or given the set of options, carbamate would definitely be the most appropriate functional group. And since we had a list of functional groups to know, and this was the carbamate, I will probably stand by this as being the correct answer for number 5. And where a carbamate in general would be something that has the nitrogen, carbonyl, and then an oxygen. Any other questions about anything? Were there any general concerns with the exam or the format? If people continue to have suggestions on maybe ways to improve, I am open to hearing them. I may not be able to incorporate all of them. It seems that the grade scope process worked very well for everyone. You would not be able to have two, you could run this reaction in methanol and only one would add in. Because as soon as you add this in, this becomes a very deactivated carbonyl or very stabilized. And it's going to be very difficult to get this dimethylamine to leave and become anything else afterwards. And so we don't have any acid or base around. This is just neutral. Whereas isocyanates are quite reactive because it greatly increases the amount of resonance in the product. This is thermodynamically downhill. Oh. So if methanol were, so the ureas have nitrogens on either side of the carbonyl, and so we don't have another way to get another nitrogen into the molecule. If we ended up adding two methanols in somehow, this would be a carbonate. Oh no, I apologize. Can I go over number 10? Absolutely. Okay. So number 10, the first part is recognizing um, where the sort of electrons coming from in the bond movement. So I am describing sort of like where the flow of arrows coming through. So if we look at these arrows, the electrons start here at this sigma bond, and this is the bond that ends up migrating over, and it will go to the nitrogen, and then the electrons break a bond that between the nitrogen and nitrogen, and this is also a sigma bond, so it ended up being a sigma to sigma star interaction. So if you wanted to draw the orbital of this, we'd end up having a sigma star here that's interacting this filled sigma bond. So if you look at where the flow of arrows start, what type of bond is that? And then at the end, what type of bond is breaking? Oh yeah, there was an even simpler answer to number 12 that had nothing wrong with it. Um, if you just made the aldehyde and then did a triple reductive amination with ammonia, you could do this all in one step, and it would go to the product. There's one person who wrote that. I thought it was pretty clever. Great job. So my intention was for people to use two different components, but I reward good answers. I think on this exam, if you ended up needing to use more than twice as many steps for a synthesis problem, then I may have taken a point off just for it being too long. There were some cases where people did about 10 steps for a synthesis that should have been done in about 3. But even those penalties aren't too severe. Can All right, I see grade requests coming in. I will get to these when I can. I don't see any new questions on Piazza. to maybe continue to review just the exams more generally, most people who had some points missed on number 12B likely didn't recognize that the product had 3 carbons on one side, 3 carbons on one side, and then 4 carbons on the other. This means to start from a 4-carbon building block, we really need to somewhere break this double bond in half in order to give one of the right components. Then if we're thinking about making esters, using DCC and DMAP from alcohols and carboxylic acids is usually the fastest way. And that means we need this anti-Markovnikov hydration of the double bond. The thionyl chloride mechanism was pretty much out of the notes. As described, I think that wasn't too surprising. Maybe I'll do a quick commentary on all of it. If there are any other questions, if you want to hear. For number 1, we go through, we look at the different hybridizations. We have 2 sp hybrids that we can get rid of. We have 3 that are sp2 hybridized. These will be the ones that are best stabilizing positive charge. We see that on B, we can have a variety of resonance structures after protonation. This should have been a reaction arrow. So we can put the positive charge on 2 different nitrogens. For D, it would have been putting the positive charge on an oxygen nitrogen, which would have been worse. And A isn't able to share it on another heteroatom. We discussed 2 some. 3, a quinoline is a quinoline. Lithium aluminum hydride is the only one that can reduce carboxylic acids. We just discussed 5 a bit. The beginning of class, I went over 6 briefly. For problem number 7, I think the element that maybe people maybe tripped them up the most was recognizing that this carbon migrates to this position. So we end up with a isocyanate where the nitrogen is directly attached to the phenyl. That means after addition you get A rather than something like E. Dibol will be protonated by a carboxylic acid. So you'll lose hydrogen. Then you'd end up with an aluminum salt that looks like this. And another lithium aluminum, another dibol isn't able to come in and coordinate and react again in order to kick it out. I think I have that on the reaction matrix. If it's wrong on the reaction matrix, then I'll give you that point. In this following sequence, we have, this is just an SN2 reaction. We end up putting the nitrile on that carbon. Base with an acid and an alkyl iodide will make an ester. And then excess dibol will reduce the ester and the nitrile both to aldehydes. So that gives us a bisaldehyde. The big idea here probably is making sure to recognize that this nitrile is adding on another carbon so that we don't accidentally choose B. Probably the most commonly mistake on 9 was choosing E instead of B. I think making the oxime and then reduction gives you a primary amine. So even though this is an ethyl here, there is another carbon on the aldehyde. So we'll end up having 3 carbons after the reductive amination rather than just 2. Talked about this. Nitrogens can only go to quaternary ammonium salts. We can't make 5 bonds even though we have 3 equivalents of the alkyl halide, and it will continue to make a positively charged ammonium salt. P2O5 is our reagent to dehydrate to nitriles. The polymer that comes from here, this is a dehydration reaction overall, so we just need to go and put another OH at the end. So really all you had to do was just take the brackets off this exact molecule. Number 8. So sodium cyanide does an SN2, and it displaces the bromide to give 1. When we have base and an alkyl halide in the presence of carboxylic acid, this will introduce the ethyl ester. And then esters are reduced to aldehydes, and nitriles are reduced to aldehydes when you react them with diol. And so by adding in this nitrile, we add on another carbon. That's why we get to D rather than something like B. And I think the only one I haven't made a comment on is D. And we know that if we have a normal anhydride, it'll go to 2 alcohol molecules. That means that both of these will end up going to 2 alcohols, and they're going to be connected by this carbon chain. And this ketone also will be reduced by the lithium aluminum hydride. Oh. My best advice to you right now, I can go and sort of talk about it again, perhaps a bit on Friday. Now our time is up, so I should probably let people get recouping and perhaps prepared for another class. I would say, I think on all the different problem sets, exams, extra practice exams, I would just get the blank versions of those and look at those problems and maybe redo them. I imagine you haven't had all those just completely memorized. That would be the first thing I would suggest doing. All right, everyone, I am logging off. Hope you all have a good one.